Welcome to our next lecture on operator-valued free probability and non-commutative distributions. So last time, we looked on operator-valued semicircular distributions. In particular, we saw that if we take free semicirculars, let's say scalar-valued free semicirculars, and we are putting them into matrices, we get an operator-valued semicircular element. And with operator-valued semicircular elements, we know how to deal with them. So we can calculate, in principle, numerically at least, their Cauchy transform. So this means we understand more or less their distribution. Today I want to change the perspective a little bit and look on another question, which maybe looks more difficult and maybe more interesting, namely polynomials in free semicirculars. So I mean, we already saw that we can deal with the sum of guys. Okay, but if we have nonlinear problems, a priori we only know that the distribution of such polynomials in free semicirculars is determined, but we don't really know how to calculate it. And today I want to show that actually those two problems, understanding matrices in free semicirculars and understanding polynomials in free semicirculars, are related. And that's the idea of linearization, a very powerful idea which I want to address today. So I mean, our goal in the end is to understand polynomials in free semicirculars. Maybe later we want to do more general free variables, but at the moment we want to do semicirculars because there's this idea of linearization which tells us that this problem, polynomials, is the same as understanding matrices in the free variables. And if the free variables are semicircular, then we understand the matrices in them. Matrices in other free variables we don't really understand so well at the moment. Good, but we will come back to this. So let me first make those remarks. So what we can deal with at the moment, so that was the last what we saw in the last section. So we saw that we can deal with linear matrices in free semicirculars. We can deal with linear matrices, and we wrote them of the form. So S is this matrix, and this is a matrix where the entries contains free semicircular. So we wrote them as B1 tensor S1 plus and so on plus BD tensor SD, where the B's are just ordinary matrices over the complex numbers, let's say n by n matrices, and S1 up to SD are free semicirculars in a scalar-valued free probability space, in a scalar-valued C-star probability space, let's say. So this is a linear matrix in free semicircular variables S1 up to SD. And here I'm taking scalar-valued ones. Okay, and maybe the first thing which I want to see is that actually we can generalize this a bit by adding just a constant matrix here, because this means we are just shifting our variable, and on the level of the Cauchy transform this only means a shift in the arguments. So this we are still dealing with the same Cauchy transform. Okay, so the first point is that we can go over from linear to affine, which means there's an additional constant term. So note that we can also consider affine matrices where we add to this an additional, let's say, matrix B0, also just a matrix, ordinary n by n matrix. So matrices by adding a constant, let's say B0, an ordinary matrix, matrix times 1. Okay, and this is just, we can deal with this more or less in the same way, because this is just a shift in the argument of the Cauchy transform. Since this gives only a shift, in the argument of the Cauchy transform. So this is like in a classical case, if I have a probability measure and I'm just adding a constant, then I'm just shifting the whole probability measure just by this constant. And of course, the Cauchy transform or the Fourier transform of the shifted guy is expressed very easily in terms of the unshifted one. And the unshifted one we can deal with. So in our case, this means that if I take the Cauchy transform of this shifted guy, so I'm adding to the S, which is the linear matrix, I'm adding, let's say, B0, or more precisely B0 tensor 1, plus S. So this is now my random variable, S plus this B0. So and I want the Cauchy transform. So this means I have to evaluate this, an argument B, which is an n by n matrix. So this, by definition, of course, is our conditional expectation, which is identity tensor phi in this case. And then I'm taking my argument minus the variable, and the variable is B0 tensor 1 plus S, and I take the inverse of the whole thing. And to this I apply this identity. Okay, good. But of course this here, I mean this B here, of course, is the same as B tensor 1. No? So of course that's the embedding we're always doing. So I have here B tensor 1 minus B0 tensor 1. So this means I just can add this to the argument. And so I just have a shift of the argument. So namely this is now B minus B0 minus S. So this here, without taking the inverse. This is now, you see the Cauchy transform of my variable S, the linear matrix, but at this argument. So this is GS of B by minus B0. And of course, GS is something which we can calculate. That's what we talked about. The only point to see is that the argument is still in a domain where we can deal with those guys, namely in the upper half plane. Okay, but of course, if we are looking on our random variables, they are always self-adjoint. So I mean the B1 up to BD had to be self-adjoint. And this means we should also add a self-adjoint B0. So the B0 we are adding here is self-adjoint. So since we consider self-adjoint random variables, so we need also that B0 is self-adjoint. So because I mean S has to be self-adjoint and we add something and we want to have a self-adjoint thing. So the B0 should be self-adjoint. And of course this means that the imaginary part of this argument here is the same as the imaginary part of B. But B was taken from the upper half plane. So we need this. And thus we have that the imaginary part of B minus B0, so this is the imaginary part of B, minus the imaginary part of B0, but B0 is self-adjoint, so has no imaginary part. So this is the imaginary part of B0, and this, of course, is in the upper half plane of our matrices. So this means also after this shift we are still in the upper half plane, and this here is a valid argument for this Cauchy transform. So this means we can calculate the Cauchy transform of the variable S at the argument B minus B0. At least theoretically we can write down our equation, which we can solve by iteration, so at least numerically we can solve this. Okay, and then, so this means we can calculate the operator valued Cauchy transform But as I said last time, usually we are interested in the scalar valued distribution, meaning also the scalar valued Cauchy transform. But this we get just by applying the trace to those things, the operator valued guys. So this means if we can calculate the operator valued guy, then from this we can also get the scalar valued. Also the scalar valued Cauchy transform. Actually of the operator in which we're interested, namely the B0 plus S. So I mean now S is our linear matrix, we are adding the B0 and we want not the operator valued Cauchy transform of this, but the scalar valued Cauchy transform. So that's my notation for the scalar valued Cauchy transform. This of course I'm just taking at a complex number. So this is defined in the ordinary upper half plane of the complex numbers. So this set is just a complex number. The scalar valued Cauchy transform we are getting by taking the trace of the operator valued Cauchy transform B0 plus S. At this argument, of course the argument embedded into the matrices Z times 1. Okay, but this we know we can express it in terms of this via a shift of arguments. So we have the trace of G of S at the argument, and now we have Z times 1 and we are subtracting B0. And this we can calculate. And of course you see here we only have a complex number, but of course this B0 here is just an arbitrary self-adjoint matrix. So in this case we need this GS not just at a multiple of the identity, but at a more general argument. Good. Okay, so this means affine matrices in semicirculars is also something we can do. Yeah, but now I want to look on this other problem, namely looking on nonlinear problems in free semicirculars. I mean, all this here is essentially linear. Good, but what maybe we really want, and what we addressed somehow in section 5 was, so in 5.15 we saw that also for arbitrary polynomials and let's say not arbitrary, but let's say self-adjoint, because our random variables should be self-adjoint. So for arbitrary self-adjoint polynomials, let's say P, so this is a polynomial in the formal variables x1 up to xd over the complex number. We can apply this polynomial to free semicircular elements, and then we want to know what is the distribution of this. And we saw that this is uniquely determined because we know the distribution of each of the variables. It's semicircular and they are free. So we have the joint distribution, and this means any polynomial in those guys has a determined distribution. But the question is how to calculate this. Up to now we only know it's somehow determined somehow, but we didn't have tools to deal with it. But now we want to do this. So we know that this for a given P, the distribution of this polynomial applied to our free semicirculars so taking this polynomial and plugging in the free semicirculars, and the distribution of this is uniquely determined by the fact that I have semicirculars which are free, but the question is how to calculate this. However, up to now it is not clear how to calculate this distribution. How to calculate this. Good. Okay, and so what we want to see now, what I want to show you, is that actually we can attack this problem by relating this problem of a polynomial with the corresponding problem in affine matrices. Right? In affine matrices, we can deal with them. So we will now see that we can do this. So tracing or calculating the distribution of this polynomial by actually relating this problem, which is a polynomial, a nonlinear problem, with a corresponding problem in matrices. And we have affine matrices with a corresponding problem in affine matrices. Good. And before I do this in full generality, let us look on example. Let us do how this works in example. And then later we will do this more abstractly. Okay, so I'm taking a, let's say, a polynomial in two variables, and I'm taking, let's say, a quadratic one to make it as simple as possible. Of course, it should not be linear, and it should be a quadratic one which somehow has no apparent factorization property. And so the polynomial I'm going to use is x1, x2 plus x2, x1, and then I'm also adding a square, let's say, of x1 squared. Good, so this is our example. And there we want to see what we can do. Okay, so we consider as a polynomial, so d is equal to 2, so I have two non-commuting variables, and I consider the polynomial x1, x2 plus x2, x1 plus x1 squared. So it should be a self-adjoint polynomial. So this means the star of this, if the x's are self-adjoint, should be p again. So this means if I have this term, I also need this term. And of course, x1 squared is also self-adjoint. Good, so in this polynomial, I'm plugging in my semicirculars. And so what I get, I just call p, which is my polynomial applied to S1, S2. So I have here S1, S2 plus S2, S1 plus S1 squared. Good, and so what I want is actually the Cauchy transform of this p. I mean, I want a distribution of this p, which means I would like the scalar valued Cauchy transform of this. So a distribution of p, and of course, we should note that p is self-adjoint, because otherwise, of course, it's not so clear what distribution should be. We're only dealing with self-adjoint guys, so the distribution of this p is given by its Cauchy transform. This is now just an ordinary Cauchy transform on the upper half plane in the complex numbers. So this is Gp applied to Z. Z is here a complex number, and by definition this is just phi applied to Z minus P inverse for Z in the upper half plane of the complex numbers. Good. Okay, and I mean, writing it like this, there's actually nothing we can do. I mean, this is a, I mean, the P is built out of the S's about which we know something. So of course we know somehow Cauchy transforms and maybe also joint distributions of them in some sense. But there's no clear way of relating this with the distribution of the S's. Okay, and so what what we are now doing is essentially we lift this problem. I mean, this is a problem on the ground level. I mean now we start with a scalar valued problem. So our B is equal to C, and this of course is a problem on the ground level. But now we lift this to higher matrix levels where we have more possibilities of, let's say, factorizing such Z minus P and also the inverse. So what we are going to do is that we lift somehow the problem of calculating the inverse from the ground level C to matrices by finding their factorizations of P into affine terms. By finding their factorizations of P into affine terms, in terms which only contain linear or constants. Good. And the first step in this direction is actually that we can write the P. We can factorize the P into linear terms, but we have to go to matrices. So namely, I'm claiming that actually I can write the P in the form that I take, let's say, a column. So this means, so I'm going essentially here to 2 by 2 matrices, but I'm multiplying 1 times 2 with a 2 times 2 with a 2 times 1 matrix. Because P is a 1 times 1 matrix. P is just, I can identify P with a 1 times 1 matrix. So I take S1 over 2 plus S2. So this is a 1 times 2 matrix, and the entries are linear in the S's. That's the point. I want only linear guys or affine. So constants are also allowed. So here I have a 2 by 2 matrix. This is just affine or just constants. And then I'm multiplying essentially with this guy again, with S1 over 2, but the adjoint of this S2. So this is a 2 times 1 matrix. Okay, and I mean, this is now maybe looks like a miracle, but okay. So let us at least check that it works out. So if I multiply this with this, so I'm multiplying S1 times this minus this guy. So I have here minus S1 over 2 minus S2, and here I have minus S1. So this gives me a 1 times 2 matrix, and now I'm multiplying it with this. So what is this? So this is this S1 times this here. So this gives minus S1 squared minus S1 squared minus S2 S1. So this is this multiplied with this, and then I have to add this times this. So you see I'm getting another minus S1 squared over 2, and now minus S1 S2. And you see, apart from the minus sign, this is exactly S2 S1 plus S1 S2 plus S1 squared. So what I have here is exactly minus P. So I have now factorized my P into a product of matrices. And the point is that the entries of these matrices are linear. Okay. So of course this looks maybe now very special, maybe like a miracle or whatever. The point is of course that this is not special for this P. Of course we have to deal with this later. But for now let us just look on this and then see whether this helps us anyhow for in anything. So what I get here is minus P. Maybe this is my capital P, my operator. And maybe let me give names to those three guys here, because in the following it does not really depend on what they actually are, but it's just that I have a factorization like this. And of course we should keep in mind that the entries are linear. That's what we really want. But to reformulate the problem, it's just important that we have a realization like this. So let us denote the three components there. Let's say this guy here, this row I call U. So this is this S1 over 2 plus S2. This here which is the adjoint of this, which is the corresponding column I call V. This is S1 over 2 plus S2. And this guy here I call Q. Actually, I say this is the inverse of a matrix. I mean, this is, of course, for this matrix, it's itself its inverse, but it's better to call this Q to the minus 1. So this is this matrix minus 1, 0. So it's important in the following that actually what I have here is an invertible matrix. Invertible in our polynomials. In this case, it's, I mean, Q and Q to the minus 1 are the same here. Okay, but for the following things, it's better. This is the inverse of a matrix. Okay, so if I use those notations, then what I have shown you above is actually that I have this factorization of P as minus U Q to the minus 1 and V. Okay, where the U and then the Q and the V are affine in S1 and S2. Where U, Q, and V are affine in S1 and S2. So the S1 and S2 appear only in a linear form, or I only have constants there. Good. Yeah. Okay, I'm writing this P in this form. And what I really want, of course, is the inverse of P. So you might think, okay, maybe if I'm taking the inverse of P here, I should take the inverse of this product. But of course, this doesn't make much sense because those guys are not invertible. Okay, so I mean, just taking now directly the inverse of this is not what I want. But what I should do is that I should now lift the calculation of calculating Z minus P inverse with the help of this decomposition into 3x3 matrices. And then using essentially all the structure which I have here. So let me do this in the following. So what I'm going to do now is to do the calculation of Z minus P, which is a calculation which should be done a priori on the ground level. I'm doing this calculation on a higher level, namely on a level of 3x3 matrices, where I use somehow the fact that I can factorize P in this form. Good. Okay, so what I'm going to do is the following. Yeah, so I'm looking now on the following problem. So what I really want is Z minus P. I want the inverse of this. Okay, I cannot deal with this. So I'm putting this into a bigger matrix, where here I'm also putting this Q. This Q coming from this factorization. This Q is now a 2x2 matrix. So here I'm looking now on the problem of a 3x3 matrix. Of course, calculating the inverse of this is essentially the inverse of this and just the inverse of this. Q is invertible. Okay, so taking the inverse of this is something which in principle is the same as taking the inverse of this. Yeah. Okay, but now we will see that in this form we can really factorize this matrix into again simple terms which only involve linear stuff. Okay, so let's see. So I'm claiming essentially that I can write this. So building on the factorization which I have for the P, that I can write the P like this. I can actually now also factorize this 3x3 matrix in the following form. So this is 1 minus U Q to the minus 1, 0, 1. So this is one matrix times Z minus U minus V minus Q times 1, 1, 0. Here I have minus Q to the minus 1 V. Okay. And for this, I'm just using this factorization of P. Okay, so let us check that this is okay. So let us calculate. So what is the product of this? So this is Z. So you see this is Z minus this guy. We have here minus minus, so it's plus U Q to the minus 1 V. And you see this is P. This is Z minus P according to this factorization. Okay, so this is this term. Then here I get minus U, and here I get U Q to the minus 1 times Q. So I get also U, but with a plus sign, so actually here I get 0. But because terms cancel here. Okay, here I get just minus V, and here I get 0 minus Q. Okay, so that's a multiplication of the first two. And now if I multiply it with this, so you see I get here this times 0. So I get exactly this term, but this is Z, and this here is minus P, according to this factorization which we have here. P is minus this guy. Okay, so this Z minus P is okay. Here I get 0 times 0. 0 is okay. And here again I get a cancellation. So namely I get the minus V. And here again I have just the minus V written in a complicated form that I have it as Q times Q to the minus 1 times V. And again, the sign is a plus. So it also goes away here. And here I'm just left with the minus Q. So you see this factorization of P into this row matrix column. If I put those guys into a bigger matrix, then it gives me a factorization like this. Okay, and now, so this is just a factorization of Z minus P. What we want is the inverse. So I have essentially factorized this into a term of product of 3 terms, and the point is that the first and the third term are of a very specific nature, so namely they are of a triangular form, and I have ones on a diagonal. And this means those guys are invertible, independent of what this here is. So triangular matrices of this form are always invertible, and one can write down very easily the inverse. So this means since the first and third factor are always invertible, so this, I mean, what I have here is a matrix of the form 1, 1, 0, and here I have something, let's say A. And such a matrix is always invertible, and the inverse is essentially the same. I just have to put a minus here. So this is 1, 1, 0, minus A. Because if you multiply, you see you get 1 here, and here if you calculate, you get minus A plus A, so you get 0. Here you get also 0, and here you get the 1 again. So this is just by simple calculation the inverse, independent of what A is. So A doesn't need to be invertible or whatever. And of course this is here, I mean, this here is a 3 by 3 matrix. So in this form. So I mean, this is a 1 by 1 identity matrix. This is a 2 by 2 identity matrix, and this is true here for any sizes which I have. Good. Okay. So this means I can write down now the inverse of this. This is of course the inverse of this product, but this is the product of the inverses in the other order, and this guy and this guy can invert very easily. Just write it down. So essentially the inverse of this is reduced to the inverse of this matrix. And this matrix, you see, this is really now a matrix which is affine in S1 and S2, because the V and the Q and the U were affine. And Z is just a complex number. So this means, so what we get from this factorization is the following. That if I take the inverse on this side, and this is really what I want, because in particular the entry, the 1, 1 entry is what I want, and of course here I get just the inverse of the Q, and the Q was invertible. That's important, that in my factorization here I have a Q which is invertible. So you see I need the inverse of this. Yeah, so this is the inverse of this matrix, which is the inverse of this. And this we can write as the product of the inverses in the other order. So first we get the inverse of this guy, which is 1, 0. The minus goes away. I mean, of course, if the A is here, then it will also appear here with a minus sign. Huh? So I have here the Q to the minus 1V, 1. So that's the inverse explicitly written down. Then the inverse of the second term, which of course we cannot write down explicitly. So I'm just writing Z minus U minus V minus Q inverse 1 U Q to the minus 1, 0, 1. This is the inverse of the first term, just taking away the minus sign here. Okay. And you should also see that actually I'm writing here the inverse, but the inverse of this matrix exists because we know that this inverse exists. So because I mean this is self-adjoint, Z is a complex number, so we know that this inverse exists, and by assumption the Q inverse also exists. So the inverse of this exists, so this means this inverse here really exists. Yeah, and maybe now you see I have here the P, and I consider this as a function of Z, and the Z only appears here. So maybe let me also give an abbreviation to this. So namely this matrix of which I'm taking here the inverse essentially is the matrix where I have Z and 0 on the diagonal, and then I'm subtracting the matrix which has all the other guys which are independent of Z. So maybe I should give names to this. So if we put P hat, let's say, this is the matrix which contains all the other terms here. So this is 0, and let's say U, V, and Q. And lambda of Z is the contribution coming from Z. So this is just Z 0, 0, 0. Then this guy here, without the minus sign, is actually lambda of Z minus P hat. So what we have seen above is that actually this Z minus P to the minus 1, 0, 0, minus Q to the minus 1, this matrix is actually the inverse of this times the inverse of lambda Z minus P hat times this. Okay, but now you should see what we really want of this matrix is just the 1, 1 entry. I mean, the other entries we know those are 0 and this is Q. So, but what we want is the 1, 1 entry. So how do I get the 1, 1 entry of this product? And you see, because I have a 0 here and a 0 here, the 1, 1 entry of this product exactly is the one coming from here times the 1, 1 entry from here times the one from here. No other contributions. Which means that what I have here is a matrix where the entry here is exactly the 1, 1 entry of the inverse of this matrix. So this means I have here in this matrix here, I denote it now by lambda of Z minus P hat. I'm taking the inverse of this. This is the whole matrix, but now I'm taking the 1, 1 entry because this is exactly the guy which appears in this product. So of this guy, so this is a priori a 3 by 3 matrix, but I'm just taking the 1, 1 entry, and then I have other guys here, okay, which of course here are 0. I know what they are, but the point is that this 1, 1 entry here, which is this guy, which a priori might not be so clear what this is, actually I can get it by taking the inverse of lambda Z minus P and taking the 1, 1 entry of this. And I mean this matrix here has other entries which are complicated. which if I do this multiplication, they will give 0 and such things, but a priori, the other entries of the inverse of this matrix might be complicated things, but I don't care about them. Because the only thing which I really want is the 1, 1 entry, because this shows up here. So this means from this calculation, we have a way of writing down the Z minus P inverse in a form which involves those matrices here, and they are linear, they are affine matrices. That's the point, that we re-express the inverse of Z minus P in a form which involves affine matrices. So and this means, of course, now that we can also, what we really want is applied phi to this guy. So we have to apply phi, but we can now also do this on the level, on operator valued level. Yeah, so what we see from this is that this inverse of Z minus P actually is the 1, 1 entry of the inverse of such a matrix. So what I have is that Z minus P inverse, that's a quantity in which I'm interested, which I need for calculating the Cauchy transform of P, that I can also get this by taking this lambda set minus P hat. This is in our case a 3 by 3 matrix. Taking the inverse of this, the inverse of this is 3, is still a 3 by 3 matrix, but of this inverse I'm only take the 1, 1 entry. All the other entries I don't care about, but I know that the 1, 1 entry of this is exactly this guy. So this is the 1, 1 entry of the 3 by 3 matrix which I have here. Good. Okay, so this looks quite good, but it's even better that this also fits with applying now our state, because it's not just the inverse which I want, but what I want is the Cauchy transform, the scalar valued Cauchy transform of P, so GP of Z, which is phi applied to this. So this is phi of this thing here, Z minus P to the minus 1. Okay, and now we know this is the 1, 1 entry of this. So what I'm doing here is, of course, taking phi of, so I have here lambda of Z minus P hat to the minus 1. This is a 3 by 3 matrix. Of this I take the 1, 1 entry, and to this I'm applying phi. Good. Okay, so what do I have here a 3 by 3 matrix. I take the 1, 1 entry of this 3 by 3 matrix. To this I'm applying phi. Okay, but this is the same as applying phi first to all entries of my 3 by 3 matrix and then take the 1, 1 entry. But applying phi to all entries is just taking my conditional expectation, identity tensor phi. So instead of saying I'm taking phi of the 1, 1 entry, I can also say I take the 1, 1 entry of identity tensor phi of the inverse matrix. So this is the same as first taking phi of all entries of this matrix, lambda Z minus P hat to the minus 1. So I'm taking this and then taking the 1, 1 entry. Yeah, but this guy here is now exactly our operator valued Cauchy transform of this guy here at this argument, because this is our conditional expectation. So what I have here is just G of this p hat at the argument lambda of z. And this means we are now back to something which we can deal with, because the point is this p hat is a affine matrix. So maybe let us note this again, because this, of course, is the crucial point why we are doing all this. I mean, rewriting a polynomial just in terms of a matrix where the entries are just some other polynomials, this would not be very helpful. The point is that we rewrite it in terms of the matrix where the entries are just linear in the S's and constants, because that's something we can deal with. So let us note this again. So note that this p hat, so what was this? This was, here. We are putting the u, the v, and the q, which we had in the very beginning as this decomposition of the p. We put them into a matrix, and in our case, maybe I write it down again explicitly. So the u was a column, a 1 times 2 matrix. So namely, it was given by S1 and S1 over 2 plus S2. The v, this is a row. This was just the adjoint of this. So this is S1 and S1 over 2 plus S2. And here the Q was a 2 by 2 matrix. So when it was here 0, minus 1, minus 1, 0. So maybe this is now concretely in our example what this p hat is. And so you see, it's linear in the S1 and S2, or maybe affine. So we also have some constants somewhere. So we should note that this is an affine matrix in free semicirculars, and this is something we can deal with. So we can calculate the operator valued Cauchy transform of such a guy. So this here is an affine matrix in free semicirculars. And a matrix in free semicirculars is an operator valued semicircular element. So in this case, it's an 3 by 3 matrix valued semicircular, of course, shifted by a constant. But we saw that we can also deal with shifts by a constant. So this is a matrix in free semicirculars. Thus, it's in our case an M3 of C valued semicircular shifted by a constant. And as I just told you at the beginning, this is something which we can calculate. We can calculate operator valued semicirculars, but we can also calculate them if we shift them by a constant. So for which we can calculate its 3 by 3 matrix valued Cauchy transform. Cauchy transform G p hat of B, if B is in the upper half plane of the 3 by 3 matrices. Okay, and this might be a problem, because what are we using as an argument? We take lambda of z, and the lambda of z is of this form. And of course, I mean, this is in the upper half plane of the complex numbers, but here we have zeros, which means we are essentially on a boundary. So this guy is not really, this is not in the upper half plane of the 3 by 3 matrices. So a priori, we might not be able to use our theory, which we have developed so far. So this might be a small problem, which we should check whether this is really a problem or not. So note also that the lambda of z, so in our case it's now a 3 by 3 matrix. So it has the set, the complex number in the upper corner, and then it has zeros everywhere else. So this guy is not in the upper half plane of the 3 by 3 matrix. I mean, this guy is okay, but here the zeros, I mean, they are on a boundary. Huh? There I would be on like on the real axis. So this is not in H plus of M3 of C. And we can only calculate our operator value Cauchy transforms in the upper half plane. And we don't really know what happens if we go to the real axis. I mean, that might explode, or it's not so clear a priori. So this means a priori, our theory does not really apply to what we need for calculating GP of Z, because for this we have this argument. Okay, but we can somehow, it's not really a problem, because we just change the zeros by little epsilons moving into the upper half plane, and the only point is to see that things are continuous. And in our case, this is true because we know that the inverse which we are taking here really is well defined. We get problems with taking the Cauchy transforms if the inverse doesn't make sense. But here, we know from our calculations that this inverse here really exists at this argument, because that was exactly what we calculated before, because the existence of the inverse of this was exactly the same as the inverse of Z minus P, and that's something which we know, because Z is in the upper half plane and P is self-adjoint. Yeah, so this means we really can deform things a little bit, and things are continuous with respect to this. Okay, so this guy lambda of Z is not in the upper half plane. So this means, first of all, that our theory from section 6 for solving for G of this operator valued variable at lambda of Z does not apply directly. So we don't know whether we can get the solution by iterating. Because at the boundary, we also saw we have contractions if we are in the upper half plane. But if I'm writing down my equation on the boundary, it might be that this maybe still there's a solution and all such things, but it might not be contraction anymore, which might mean that iterations don't converge. So our theory does not apply directly. Good. Okay, but at least we know that the inverse itself exists at this point. So we know that lambda of Z minus P hat is invertible, is by the above calculations invertible, because that's exactly what we showed here. We have this is this, and this is invertible anyhow. So this inverse here exists exactly if this inverse here exists. And this inverse here is exactly this Z minus P hat. And on this side, the inverse, because this exists by our construction, is exactly the question whether this exists, but this exists if Z is in the upper half plane. Okay, so we know that this guy is invertible. And we know that the function, the operator valued Cauchy transform, is holomorphic on the set where things are invertible. Of course, usually we restricted things to the upper half plane because there we know that everything is invertible. But we also, in the beginning, we looked on analytic functions, the function given by taking the inverse, and we saw that this is an analytic mapping where the inverse exists. And this means here, because the inverse exists here, it also exists in a small neighborhood, and the function is analytic there. And in particular, this means it's continuous there. This means we can perturb it by a small epsilon, and then we know if we send epsilon to 0, we will have convergence of the values. Okay, so the function GP hat of B is holomorphic, and thus also continuous in particular, in a neighborhood of the point in which we are interested, So namely if this point lambda of z, and thus we have that I can approximate this point out of the upper half plane by perturbing things by I epsilons, and then we know that I really converge to the corresponding Cauchy transform. So we have that G p hat of lambda of z, that's what I want, which I might not be able to get directly by solving my corresponding quadratic equation, but at least I know, because the function is continuous, I get it by a limit epsilon going to 0, where instead of this argument lambda of z, I'm taking G p hat, an argument where I perturb this by an epsilon, where I'm moving into the upper half plane. So this means this epsilon, this lambda epsilon of z. So this is, so I have z here. The problem is where the two zeros here, and I'm moving those zeros into the upper half plane by taking I epsilon at both places. Okay, and so if epsilon is now bigger than 0, this is now really, for each epsilon bigger than 0, this is a matrix, a 3 by 3 matrix, which is in the upper half plane of the 3 by 3 matrices. So for those, I know how to calculate such guys. So this here, and this converges if epsilon goes to 0, of course, to my lambda of z. But this guy here is in the upper half plane. So so this matrix here is really in the upper half plane of the 3 by 3 matrices for any epsilon bigger than 0. And this means we can calculate, for each epsilon bigger than 0, we can calculate this operator valued Cauchy transform, and then we send epsilon to 0, and then we get this one. Okay, and from this one, we get, by taking the 1 entry of this, we get really the scalar valued Cauchy transform of our original polynomial. Good. Okay, so this shows that, at least in this example, we really can lift our problem of calculating the Cauchy transform of a polynomial to somehow calculating an operator valued Cauchy transform of a kind of linearization of this polynomial, of taking a matrix, which of course has something to do with our original problem, but which is linear in all the s's. Good. And of course, the important point now is that this is nothing which is specific for this example which I showed you, but this is something which works for all polynomials. Okay, and the main thing which we needed was that I wrote this p as this u q to the minus 1 times v. So, and I mean, all the rest which I did in this calculation did only use this factorization. Okay, so what one really has to see, if one wants to imitate this for any polynomial, is whether I can do this factorization for general polynomials. So let me first write this down as a remark, and then we will define it precisely what I mean with this, and then the main point will of course be that for any polynomial I have such a linearization. So the main ingredient in the calculation which I did above, in the above calculation, was that we can factorize our polynomial in the semicirculars as P, so I wrote this as minus U q to the minus 1 V. Where this was a matrix which is invertible, and those were rows and column vectors. And of course the point was that the U, the Q and the V were affine in the semicirculars. Just constants or linear terms with affine U, Q and V. Yeah, and so what I want to point out now is that this is was not a miracle for this example, but this is really something which is true in general. So this factorization, this works for all polynomials. And actually, of course, this has nothing to do with the fact that I was plugging in semicirculars in my polynomials. This factorization was just a factorization which works just for formal variables. So actually, this is a factorization on the polynomials in non-commutative variables. Okay, so it works for all polynomials and is actually independent from having semicirculars here. Of course, our point of having semicirculars was that I'm going over to a matrix where I have my variables, and at the moment I only understand matrices of semicirculars. So that's okay. Later on we can see whether we can also do something for other free variables. But at the moment, if we really want to deal with the matrices, then we should have operator-valued semicircular guys. But for this factorization, having semicirculars, this doesn't play a role. And so this is actually independent from having semicircular elements as our variables. Okay, so let us now generalize this whole setting to the case of just formal variables. So let us now do the general case on the level of formal variables. And those are, of course, our non-commutative polynomials in, let's say D non-commuting variables x1 up to xd. Good. And so let me maybe now first define what I really want. So that what I did before, that this really works. And this is what we call formally a linearization. So for a polynomial, I want a linearization, which means I want this factorization of my polynomial as this minus u q to the minus 1 times v, where the u, v, and q are affine guys. Okay, so that's first, we make a definition out of what we want, and then hopefully we have a theorem which tells us that we always get what we want. And of course, this factorization is on the algebraic level. This has nothing to do with free variables or applying states. It's just if we have this factorization, at the end we can apply our states and get statements about the Cauchy transforms. But the crucial ingredient is this algebraic factorization. Good. So what do we want? So we put this in this definition. So we are starting with an arbitrary polynomial, let's say p. So this is a polynomial in non-commuting variables, x1 up to xd. And self-adjointness also doesn't play a role for now. Of course, at one point we should see that if I have a self-adjoint polynomial, I get also a self-adjoint linearization, because that was, of course, important in the applications. But just for doing this factorization, I can have a general polynomial. So this should be given. And then I want this u, v, and q and I'm putting it directly into the matrix which we really use. The linearization, I'm taking this u, v, and q and putting it in a matrix, which I call then p hat. So this should be the 0, u, v, and q. That was the matrix which we used before, which really was our operator-valued semicircular. So okay, so such a matrix, which is a matrix of some size n, where the entries are just polynomials in our variables. Okay, where of course we want a few things. So first of all, let us just be very general. So n is just any size. I mean, before it was 3 by 3, but okay, of course it could be higher. And the q, okay, so how was it before? So I mean, this here was a 1 by 1, this here was a column, and this was a row. So q has a size n minus 1 times n minus 1. So this q should be a n minus 1 times n minus n minus 1 matrix. So this should be a matrix, let's say a priori, over the polynomials. Of course, we will soon require that all things are affine, but let us first start with this. And it was crucial that it is invertible. And invertible as a matrix over polynomials. So it's invertible as a matrix over polynomials. So it has an inverse, and the inverse is also just a matrix where the entries are polynomials. Okay, so this is Q, and then U and V, those are just rows and columns. So V is a 1 times n matrix, and U is a n times 1 matrix. So U is a 1 times n matrix over my polynomials. So this is a row vector, and V is a column vector, which means an n times 1 matrix, and V is an n times 1 matrix also over the polynomials. So this is a column. Good. Okay, so this is very general, and now such a matrix we call a linearization of P if, okay, first of all, it should have linear entries, and of course it should have something to do with P in the same way as we had it before. So this is called a linearization of P, and this means two things. First, of course, it should have this linear or affine structure, and of course it should have something to do with P. Up to now, P has not really shown up. So if the following holds. So first of all, it should be linear, which means that this P hat actually is an affine matrix, which means that the U, V, and Q are also just having constants or linear entries in S1 up to SD. So P hat is an affine matrix in my formal variables x1 up to xd. More precisely, this means that I can write it as a linear combination of x1 up to xd with just ordinary matrices as coefficients and a constant matrix. So this means there are B0, B1 up to BD, which are n by n matrices over C, so just ordinary matrices, such that I can write the B hat as B0, let's say tensor 1, plus B1, tensor x1, plus, and so on, BD, tensor xd. So this means this is a matrix which only contains complex numbers. This is a matrix which only contains x1 as linear terms at various positions, and so on. So this means this really altogether is a matrix where each entry is a linear combination of the x's plus possibly a constant. Good, so that's the linear structure. That's why we call it linearization. And why is it linearization of P? Because P is given in terms of this U, V, and Q exactly as we had it before. So namely, I want to factorize P as minus U, Q to the minus 1 times V. So there in the P hat, the Q appears, but we assume that the Q is invertible. And here we take the inverse of the Q. So this is a matrix where the entries are polynomials in our variables. So this is a 1 times n. No, actually, the U and the V are not 1 times n, but 1 times n minus 1. So rows and columns. So n minus 1. So this here is 1. This is n minus 1. This is 1 and n minus 1. Okay, so I'm multiplying here 1 times n minus 1 with n times n minus 1 times n minus 1 with a n minus 1 times 1 matrix. So I'm getting a 1 times 1 matrix, which is just an element in my polynomials. Good, and now, so that's what we want. And now the theorem is that we really can always get what we want, namely any polynomial has a linearization. And the proof of this is actually, it's algorithmic. So essentially it tells you how you can produce such a linearization. And it's actually not very hard. You just have to build your polynomial out of sums of monomials. And you have then to give linearizations for monomials. And then you have to say how, if you have sums of things and you know how to linearize each of them, how you get a linearization for the sum. And this means, of course, that the matrices which you might get could be very large. But we don't care about this. We are not saying that we are producing a linearization with maybe small matrices, as small as possible, but just any. And of course, the linearization is not unique. There can be many. Good. Okay, so here's the theorem. So for any polynomial, P, polynomial in non-commuting variables, x1 up to xd, there exists a linearization. There exists a linearization P hat. Good. And for us important is that we also have a possibility of preserving self-adjointness. Okay, so I mean, with this theorem, it might be that I start with a polynomial which is self-adjoint, but I get a linearization which is not self-adjoint. And our algorithm will produce such things. Our algorithm a priori doesn't preserve self-adjointness, so we should make sure that we can repair for this. So this means if P is adjoint, I can also find a self-adjoint linearization. So let me also put this as part of the theorem, because this is important for our application. So if P is self-adjoint, then there is also a self-adjoint linearization. Good. Okay, before I give you the proof of this, maybe let me make the remark that maybe we might get here very big linearizations, and usually, of course, maybe the main interest is, or one is interested in finding maybe minimal ones, which means the matrix size is as small as possible. But this is not what I care about here. This is a different question. So remark, so such linearizations are not unique. This is hopefully clear. I mean, if you have a linearization, you might, for example, repeat it somehow in the matrix structure. So there are many ways of getting bigger linearizations. And from this point of view, it's interesting to see whether there is maybe a best one, or and best maybe in a sense that the matrix is as small as possible. Okay, and this is called the minimal one. So it is interesting in general to find minimal ones. And minimal refers here to the matrix size, this n. So where the matrix size n is as small as possible. So in the example which I had before, I realized this in terms of 3 by 3 matrices, and I think this is the smallest you can do in this case. But if you apply the algorithm, which I'm going here, you will probably produce something which is much bigger. Okay, so our algorithm in the following proof will not produce such a minimal one in general. Will not produce minimal realizations in general. Okay, but for our applications in principle, it's not really necessary to have a minimal one, because what I did works essentially with any linearization. So what do we have to do for the proof? So we have, for a given polynomial, for any polynomial, we have to find a linearization. And as I said before, a polynomial is a sum of monomials, or a linear combination of monomials. So it's enough to give a linearization for monomials, for arbitrary monomials, and then to give a way of producing a linearization for a sum if you have one for each summand. And that's exactly what we are going to do. So you build essentially your polynomial from smaller ingredients, and for the small ingredients, you know what to do, and you also know what to do for building the ingredients together. Good. So let us start with the monomials. Okay, so for monomials, we have linearizations. Okay, so I erased our linearization. So what was our linearization? Maybe just, so in general, so the p hat. So this was a 0, u, v, and q. And the condition was that p is equal to minus u q to the minus 1 v. That's what we have to find. And so you have to see, I mean, for monomials, and of course, the smallest monomials are the constants and the linear ones, and you would think, okay, I mean, they are already linear, but you see, what we have here is at least a 2 by 2 matrix form, because we want a 0 here and we want something like here. So this means even such small things must be represented in a form like this. And this means we have somehow to do the constant term and the linear term separately. So for degree 0, which means p is just equal to alpha, and alpha is just a complex number, just a constant polynomial. We can write down such a thing. So p hat. Okay, so we want a 0 here, and then of course we put the alpha here, a 1 here, and a minus 1 here. And this is now just matrix. So those are just also all complex numbers. So this is a 2 by 2 matrix. And so this means, so this here is our U, this is the V, and this is the Q. Of course, they are all linear because they are just numbers. And of course, this guy, the Q, must be invertible. That's something which you all, that may be the crucial thing. But of course, this is invertible. And of course, so what do we want? So we want that this times this times this should give our P. So I multiply here just numbers. So it's this times -1, or I take the inverse, but of course the inverse of -1 is also -1, multiplied with this 1, and then I take the minus of the whole thing, and what do I get? Is alpha, which is exactly what I want. Okay, so this is really okay. Yeah, similar for degree 1. And here you already see that we are not really respecting self-adjointness here. So self-adjoint would mean alpha is a real number equal to 1. This is really a self-adjoint matrix. What we are doing here is not a priori respecting self-adjointness. So we have to think about self-adjointness separately. Good. So what is for degree 1? So for degree 1, which means P is a multiple of one of my variables, let's say xi. So this is a degree 1 monomial. So again, I can take in the same way the p hat as 0. I'm putting the alpha xi here, 1 minus 1. So more or less it's the same. Again, this is invertible, and if I multiply this times this times this, I'm just getting minus p. Okay, so, and maybe more interesting is for higher degrees. So for degree, let's say k bigger than 2, where p is alpha, and then I have a product of variables xi1 up to xik. So what do I do with this? And I'm doing it somehow the same, what maybe you already saw there. I'm putting the x's on this anti-diagonal. So so the p hat will be a k by k matrix in this case, and I'm putting the x's on this anti-diagonal. So I'm starting here with, okay, the alpha goes here, alpha i1, then here I'm putting xi2, xi3, going up to xik. And I'm putting not the 0 here, but I'm doing the same what maybe you already saw there. I'm just putting minus ones, one below this. So I have a -1 here, -1 here, up to a -1 here, and everything else is equal to 0. Okay, and maybe to make it clearer what I'm really writing down here, let us do it concretely for the case k equal to 3, so that we maybe see it. So if k is equal to 3, I have a 3 by 3 matrix, where I have, of course, I mean, here I always have a 0. So I have here a 0, and then I have here 0, and here I have alpha xi1. Then I'm putting here xi2, and here xi3. So I have here 0, and I'm putting a -1 here and a -1 here. So I have this diagonal. There I'm putting the x's as I want to have them in a product here, and I put -1s below, and everything else is 0. So now let us see what we have there. So this is the p hat, and of course the u is now this 2 by 2 column. The v is this 2 by 2 row, and the q is this guy here. And now of course the crucial thing is this q invertible? And again we have here something, you see, I put the -1s here, so in this sub matrix the -1s are on this anti-diagonal, and this is again a matrix which is invertible independent of what I have here. So this is somehow the anti-thing of a triangular matrix. So this is invertible. So such matrices. And it's the same, more or less the same as for the triangular ones where you had ones on a diagonal. So they are invertible. So here I have essentially something like, let's say, A minus 1, 0. Where of course this can have, again, different sizes. So the inverse of such a thing is a matrix of the same form, where essentially this guy is moved over here with a minus sign. So minus A. You can check the product of this and this is, so this is 1 here. Here the a's cancel. Here it is 0, and here I just have again 1. Okay, so independent of what A is, the inverse is of this type. So that's are the matrices which I have here. Okay, so such matrices are invertible, and again, if I multiply this times the inverse of this times this, I get exactly what I want. So namely, what should I multiply? I should take minus, let's say minus, this is here 0 alpha xi1. Then I multiply it with the inverse of this, which is just moving this as a minus there. So I'm multiplying it with 0 minus 1 minus 1 minus xi2, and then multiplying it with this row. And then I should get p. But again, if you do it, you see that essentially the only real multiplication which shows up here is that this times this times this. So this is minus, and with this minus sign it is plus, so it's really exactly the p. Alpha xi1, xi2, xi3. Okay. And maybe you should think about maybe a little bit bigger matrix to see that it also fits. So, but this is the general procedure for monomials. And it's important to see that here we have matrices which are somehow invertible. That's the crucial thing. Good. Okay, so now this tells us that we can linearize any monomial, and now a polynomial is a sum of those guys. So now we should also have a way of getting linearizations of a sum if I have a linearization for each of the summand. But that's, with this structure of our linearizations, that's easy to do, because we just have to intertwine all our linearizations which we have. So assume, okay, so this is part 2, going over from monomials to polynomials. So there we assume we have linearizations for, let's say, for pi's, and they are of the form 0, ui, vi, qi. So this should be a linearization for polynomials pi. And let's say we have this for r of them. Okay, and then I want to make a linearization for a sum of the p's. So let's say we have it, I have it for all the monomials, and how do I get one for the sum? So I have for each term, each summand, and then I'm claiming that I can also write down a linearization for the sum of the p's. So this has a linearization. Okay, so what now? I'm just putting all the u's, the v's, and the q's together in a nice form, which fits together. So I mean the u's should show somehow up here, and I'm just putting them just one after the other. All the u's which I have there. And correspondingly, the v's on this side, v1, v2, up to vr, and the q's are now just showing up where they essentially belong for the linearizations of the pi's. I mean, the q1 belongs to the u1 and the v1. So I have here the q1, here I'm putting the q2, and here I'm putting the qr. and everything else is 0. And now, of course, my new v, my new u is this guy, my new v is this guy, and the q is this guy. And you see the invertibility of this big guy is just the invertibility of all the guys on the diagonal. But this, because I started from a linearization, this is given by assumption. Yeah. Okay, and if you multiply this times the inverse of this times this, then you see that you get exactly the sum of those guys here. Yeah. Okay, sum is quite easy. Good. Okay, but now the point is that what we are doing here, more or less all the things which we did here, do not respect self-adjointness. So maybe let me just finish with this. So what somehow I have to repair that if I start with a self-adjoint guy, I get here linearization, but this is not self-adjoint. So I should repair this somehow by improving this to a self-adjoint one. So what am I doing if P is self-adjoint? Of course, if P is self-adjoint, P is the same as P star, and P star also has a linearization. So the idea is that if P is self-adjoint, then P is equal to P plus P star. So essentially, I should make a linearization of P plus P star. Okay, so if P has a linearization, let's say 0 u v q, then of course P star has a linearization which is given by the adjoint of this 0 v star u star q star. So somehow this fits. I mean, if v is a row here, is a column here, then v star is of course a row. So it fits at those places. And then P star has this linearization. And if P is equal to P star, then it doesn't mean that those two guys are the same. So if P is equal to P star, then we want to take a linearization of P, but writing P as 1/2 of P plus P star. I mean, if P is equal to P, of course, P is the same as this. But if I have produced linearizations, I might not have produced a self-adjoint one, but I have one for P, and I also have a formal one for P star. And so I should hope that if I put those two guys together, I get a self-adjoint one. But of course, if I'm doing it as I did it here before, this is not going to be self-adjoint. So I have to do it in a different way, which respects the self-adjointness. And this is the following. So I mean, so I want to do a linearization of P plus P star for those two linearizations which I have, one for P and one for P star. The construction in 2, however, does not give a self-adjoint P hat. But instead, we can do something else. So instead, we take the following one. So namely, I take, okay, this 1/2, and then I have take here yeah, I'm taking here U and here V star. So that's okay. U star V. Okay, that's the same thing I would do here. But now I would put the Q's on the diagonals. But this, if I'm putting Q and Q star on the diagonal, this doesn't give me a self-adjoint thing if the Q is not already self-adjoint. Okay, but in this situation, I can put the guys on the off diagonal. I can put the Q star here and the Q here. And this gives me, of course, a self-adjoint realization. So this whole thing is now self-adjoint. And the Q in this case, the new Q, is this guy here, which again is invertible, if the Q was invertible. And you can check again that this is the right thing. Yeah, and actually, I mean, in 2, I mean, even this, if we would have used the construction from 2, we would have put here U and V, and here, V star and U star. Okay, but even there we changed it. So because we also need self-adjointness here. Okay, and then we can also change things here so that if we calculate the P corresponding to this, we will get exactly this. Good. Okay, so maybe in an assignment we can check 1 or 2 more examples of this, or really maybe work a little bit with this. But in principle, you see that this algorithm is very easy. So it really, it's just, if you know how to do it, it's very easy to do, and it's also very easy to check that everything fits together. So it's a very surprisingly easy algorithm, which is surprisingly powerful in its applications. And next time maybe I am coming back to the applications. Okay, so thank you.